Hey everybody. In this lesson, we are looking at radioactive decay, and that'll lead to us being able to talk about nuclear energy, which obviously fits into our energy unit, and it's the end of our energy unit actually. So a bit of chemistry view before we get going on that. Obviously, we hopefully know that nucleuses or nuclei are made up of protons and neutrons jam-packed in the nucleus. So protons and neutrons, and then the electrons kind of orbit around, or we act like they do at least anyways. They're loosely attached. And electrons are attached to the nucleus since, of course, opposites attract, right? And so if you're looking at force vectors, you can picture it like this. It's more complicated than that, we know, but it's a good model. And so the question I wish a lot more people would ask would be, and you can maybe pause the video and think about like, what else should someone ask if they're told this as a model for the atom, okay? And really what you should ask is, why don't those positive protons that are packed in the nucleus repel? They certainly should. They're both positive charges. Likes repel, right? So the laws of electric charges is that opposites attract and likes repel. The answer is, of course, they're held together by an even stronger force called the strong nuclear force. A page from a textbook describes, the electrostatic force was understood for hundreds of years, and it wasn't until the 1930s that started to realize like the strong nuclear force exists and learn about it. So don't feel bad if you weren't a student in the class that caught that weird kind of inconsistency. Hey, the electrons attract, because opposites attract. I wish more people would ask, well, wait, why don't those positives repel? So yeah, there's your atomic structure. Just something to review from chemistry is that the small number with the atomic symbol is your number of protons. The larger number is protons plus neutrons. I'll come up later in the lesson. And this number of neutrons here, 0.01011 business means that sometimes, the next most common number of neutrons would be there's an extra neutron. That makes the average be more than 12 instead of being 6 protons and 6 neutrons, being an exact mass of 12 always. If you average out thousands of carbon atoms, it ends up being an average mass of about 12.011 because there's extra neutrons sometimes, right? And those are called isotopes of the element, the atom. And so why is it possible for that number of neutrons to vary? Well, it's really just because those neutrons are there to help hold the nucleus together. So think of it like glue. You can have a little bit of glue or you can have a lot of glue, you can still stick stuff together, right? In fact, they're there to help glue it together, and as a result, they exchange particles that are to do with the transmission of the strong nuclear force. We'll learn more about that later in physics. They're actually called gluons. That's the extent of a physicist's sense of humor, I think. But yeah, so if we're looking at, just to make sure we're fully aware of all the ideas here, if we're looking at an atom of lithium, we have the 3 protons. This is an average mass of about 7, so the most common lithium atom would have 4 neutrons to go along with those. And so there's basically the nucleus, and then we'd have 3 electrons that would be bound to it electrostatically as well. And you think of that as a stable lithium atom. And so the number of neutrons can vary, but as long as there's enough neutrons paired up with, or protons and neutrons being paired up, because neutrons by themselves are not stable. They're stable when they're paired up with other hadrons or other baryons, really made up of 3 quarks. Barion's the type of hadron. Those fancy words you'll learn more about when you go and study particle physics more and more. I'm just using them because they're correct to use. Don't stress out about them. Okay? But yeah, we're just talking about types of particles, and neutrons and protons are baryons. If you want more information or just sort of details about the idea of formation of atoms and so on, these are videos to do with it, but I don't really think it adds a ton, so I'm not going to play it here. This one too shows, the proton-neutron soup, the early formation of the universe. So there weren't atoms yet because everything was so energetic, they're just all bouncing around freely. As things spread out and start to cool down, neutrons and protons started to lump together, and atoms started to be formed, and so on and so on. Okay. So how was this kind of discovered? Henry Becquerel discovered radiation by accident, having a uranium ore near photographic film, and found that photographic film was basically ruined as a result of being near this uranium. And he realized, he didn't ignore it, he actually looked into it and trying to figure out what it was, and he realized that chunk of rock, really, or salt, as it was here, was giving off a form of light, and it intrigued him, and so he looked into it and discovered things as a result. Okay. So just before we go further with radiation, let's just clarify there's two types of radiation. There is the super high energy stuff, which is electromagnetic. So it's gamma rays and X-rays. So it's a form of light going off. So we don't think of it as like protons and neutrons and so on. It's quote unquote just light. But you'll see later on in physics that light isn't really just light. It's actually particles as well. So it's particles of light. And then we have particulate, true particulate, if you want to think of it as, where there's actual measurable mass given off with lots of energy and so on as well. So examples of that are your beta and your alpha radiation. Okay, so you get your alpha beta, which is not as energetic. Alpha stops in like a sheet of paper or in the thin layer of dead skin cells on your body. So alpha radiation is super dangerous because it doesn't penetrate into the body and damage cells. Beta radiation is more dangerous because it can penetrate in, and gamma is obviously the most dangerous. It's super high energy. So the discovery of this stuff led to some more investigations. Ernest Rutherford discovered that oxygen was produced if nitrogen was bombarded with one of these high energy types of particles. So it turns out he was blasting nitrogen with alpha particles, which are really actually just nuclei of helium atoms. Weird, but that's what it is. And so it caused a transmutation, is what it's called, when an atom transforms into another form. It's called a transmutation. We started with nitrogen, it switches to become oxygen, gives off hydrogen as well, or gives off the proton, really, as hydrogen. And I think it's just the proton itself, not without the electron. Anyways, yeah, and so that was basically the first, the one person we're talking about anyways, an early discovery of a nuclear reaction of some sort. This isn't a chemistry reaction, this is a nuclear reaction. James Chadwick performed a similar experiment and discovered the neutron. Right, so we found beryllium bombarded with an alpha particle would produce carbon, and then and also a neutron, and so the neutron was discovered as a result of that. So when you're here in chemistry class, that Chadwick was just discovered the neutron, he was really playing around with physics stuff to discover it. And then chemists went with it as well afterwards, of course. So the source of radiation, unstable isotopes. So stable isotopes are exactly that. They have their atoms, they have protons and neutrons, and they're stable, everything stays nice, right? Unstable isotopes, you can have either not enough neutrons or too many neutrons. And neutrons need to be paired up, right? So if there's not enough neutrons, then there's, well, actually in this case, you can think of it as simple as, there's not enough neutrons, then there's not going to be enough strong nuclear force to hold things together, and weird things start to happen, right? Things spread out, things decay, whatever. If there's too many neutrons, then you might end up with neutrons that aren't sufficiently paired up with other protons, and as a result, they can spontaneously disintegrate, which we call a radioactive decay, which causes a transmutation. I should just pause for a quick second and acknowledge that this is pretty heavy-duty stuff. It's kind of unlike anything you've seen before, probably, but that doesn't mean you can't learn, right? So we're going to see examples here soon, very specific examples about types of radiation, and we'll be able to itemize out exactly what happens with the atoms and so on when that happens, the numbers of neutrons and the numbers of protons and so on. So it's just going to take a couple tries at it. You might have to watch the video a couple times, press pause, go back, repeat it. You should be able to get the hang of it. But before we get to the nitty gritty, where it's like stuff to really, this page here, you're really going to, commit to knowing how to do, I'm going to give you a little bit of background information to you about sort of how this can happen, right? How can a neutron switch to be a proton and so on? Well, it turns out they're all made up of the same stuff, right? These baryons and hadrons are made up of quarks. And what's a quark? Well, a quark's a fundamental particle, and it's what makes up neutrons and protons. It's been discovered. Just you're being told about it instead of having to try to discover it yourself. So yeah, they're made up of quarks. A proton is two up quarks and a down quark. There's the two different types of quarks, and a neutron is very similar. It's a down quark, two down quarks, and an up quark. So the idea of these being able to like switch between isn't that crazy. They're made up of the same thing. They're almost identical anyways, right? Really, the only difference is kind of the amount of energy they have and the state they're in, right? Um, Quarks, just as a quick note here, aren't observed to be alone. So you're never going to see like 1/3 of a fundamental charge, right? The charge on a proton is fundamental charge. We don't observe 1/3 of a charge, even though quarks exist. So they call that color confinement. And it's neat that they call it color confinement because they use the phenomenon of red, green, blue color combining to be white, like no color, as an analogy similar to when we say positive and negative charge. Positive and negatives neutral. They used a mathematical analysis there of just positives and negatives can add to zero. So a positive charge and a negative charge adds to zero. That's just an analogy, right? And or like a way to think of it. And so the same thing goes for the color version of things. In quantum physics, studying the strong nuclear force, they needed three things they would combine to nothing and neutralize. And so they borrowed the idea of red, green, blue. And they used colors. That's when quantum chromodynamics was formed, really the mathematics that describes the strong nuclear force. The confinement idea, they think of it as quarks are held together so strongly that if you pull them apart, if you take so much energy to pull them apart, by the time you get them far enough apart that they stay apart, there's enough energy there that that energy becomes energy equals mc squared. Energy and mass are the same thing. That energy constitutes a new particle, and so it literally creates a new particle. Weird, wild stuff. Yeah, but like I said, if you go on in this field, it'll become more and more less and less surprising, let's say, to you, at least anyways, right? It'll start to make more and more sense when you see how it all connects together. So alpha decay, to start out with, alpha decay is obviously a particle kind. It's the helium nucleus going off, right? So if we had plutonium-240 and decays into uranium-236, we can see that this makes sense because you got your plutonium, becomes uranium, and if you look, we got the 240 mass overall is the same as the total mass here, 236 and 4, right? The number of protons, 94. Well, there's your 94 protons still. It's just as a separate particle, right? So you got your parent atom and your daughter atom, and the particle that's given off, it looks like this. You know, there's your helium nucleus flying off, and so on. Okay, so a new atom is formed. That's called a transmutation. In general, you're going to have, you know, whatever atom you start with, you're going to have 4 less mass wise and 2 less neutron wise, right? Because 2 neutrons and 2 protons are going off and becoming that helium nucleus that flies away, right? They're flying off as that helium nucleus. Here you've got your 2 protons and your 2 neutrons. That's why it kind of, the numbers seem like there's redundancy here, because there is. This is your 2 protons, right? And then you have your 2 protons listed again. That's why there's the 4 there. So an example of this, you know, the red flag, the key thing to notice here is when it says, you know, something undergoes an alpha decay. Automatically you should be saying, oh, okay, so we're talking about a helium nucleus given off. So we should be thinking about this concept right here. Okay, we should be thinking about the idea that we're just going to reduce the mass by 4 and reduce the number of protons, the atomic number, by 2, and we're going to get our new stuff. So we start out with lead 204. Well, you look up on a periodic table that lead has an atomic number of 82. They're saying it has a mass of 204. That's what that is. That's your isotope mass. And so we're going to reduce that by 4. So it's going to become, well, it shows here, reduce it by 4, and reduce the number of protons by 2. And of course, you get a helium nucleus as a result. There's your alpha particle, right? And so, yeah, you just do that, and you end up with a atomic number of 80 and a mass of 200. So you just look up on the periodic table what the atomic number of 80, what element that is, and I have a periodic table in front of me. You can just look it up, but that's mercury. Okay, so Hg, mercury is atomic number of 80. Okay, so you'd be like, all right, so then that's mercury then. Okay, so there you go. I would look it up online, but the system's down right now, so I can't just pull up the periodic table on the screen and show you. But yeah, just find the periodic table and you'll see that mercury is atomic number of 80, and so we know that's what is produced when lead 204 undergoes an alpha decay. Right? So if you have this isotope of lead, it's radioactive. It's not normal lead. It's not the kind of lead that's, I don't know, in keels of sailboats and solder joints of old houses and so on, right? Or in old paint and so on. That's stable lead. This is radioactive lead. So another couple of practice questions for you there. Keep in mind, of course, this same concept is the driving principle behind these questions easy to do. Even though it's weird, wild stuff, talking about radioactive decay, this literally is nuclear physics. This makes it pretty easy to do. Okay. Another type of radioactive decay is the beta decay, a little stronger, a little more energetic. Okay. So beta particles are just high energy electrons or positrons. Positrons are actually just electron antiparticles. Okay. And the antiparticle of electron is simply opposite charge, opposite spin. It's going to have everything opposite, and it can actually mathematically be fully described as an electron that's just traveling backwards through time. So yeah, look forward to learning about that later on if you go on in physics. Weird, wild stuff. So the three types of beta decay. Okay, so there is beta negative, beta positive, and electron capture. Those are the three types we're going to talk about. There are others. The Sudbury Neutrino Observatory is currently investigating to seek to prove the existence, trying to prove the existence of neutrinoless double beta decay. So look into that if you're interested. Okay. So our beta negative decay. Beta negative decay is when an electron is emitted from the nucleus of a parent atom. It's symbolized by that. So it's an electron gets given off as part of the radioactive decay. And so this happens when it has too many neutrons. Well, if you have too many neutrons, one of those neutrons isn't going to be stable. It's going to disintegrate, it's going to radioactively decay, and it spontaneously turns into, this is crazy, spontaneously turns into a proton and an electron. Well, again, it's not that crazy because, again, a neutron and a proton aren't that different, right? But it can switch into being a proton, and it can give off energy and an electron. Okay, so an electron's given off. So if you do the math here, it's pretty simple where you're like, okay, well, instead of the same number of neutrons, one's going to turn into a proton. So if we look at an example here, tritium. Okay, so tritium is this, hydrogen with a mass of 3. Tritium is just hydrogen that has 2 neutrons in it instead of not having neutrons at all. Okay, so tritium has, I think maybe I have this down in a square here somewhere. Yeah, so we had 1 proton and 2 neutrons, right? And so it becomes, because one of the neutrons becomes a proton, made up of 2 protons, and then just 1 neutron because one of them decayed. So I was just going to show on the fly here, which I may as well still do, that this is 1 proton, and then this up here is the proton plus 2 neutrons, right? That's just what tritium is. So if one of those neutrons becomes a proton, then you're going to have 2 protons and only 1 neutron, right? So that's what you're going to see over here. You're going to see the 2 protons, and then of course the number here, the 2 protons plus 1 neutron, gives the total mass of 3 still, right? So you've got hydrogen or tritium, right? The version, the isotope. They don't often name, they don't always name different isotopes of things, different names, but hydrogen they do because it's so crazy different. Different isotopes of nickel and lead and things like that still look like nickel and lead, but they're radioactive. Whereas with hydrogen, it's pretty different stuff. Okay, I have a little keychain that actually glows for 25 years. It has tritium in it. It's a neat thing. Anyway, so it gives off these gives off electrons, and then those electrons actually get into phosphor. It's safe. But anyways. So this is what the picture is of it. You got your tritium, you've got your proton and 2 neutrons, and one of those neutrons becomes a proton, so there it is, and the electron gets given off. Okay. So in general, it looks like this, where it's like you're going to end up with like an extra proton. It seems like an extra proton came out of nowhere, right? But really, it's this swap between being 2 plus 1 to being 1 plus 2 kind of thing because of the switch, right? The neutron becomes, right? So this is the emphasis that we can put here. A neutron switches to become a proton, right? So that's my reveal later for emphasis business here, right? One neutron switches to become a proton, and that's a transmutation. So you end up with helium-3 instead of tritium, right? Literally, it's helium. It behaves like helium, right? Instead of behaving like hydrogen. A lot of times isotopes behave very similarly otherwise, like the helium might still make your voice sound funny, and the hydrogen still might make the pop sound if you light it in a test tube and so on, but it would be radioactive versions of it. So it would have this added bonus of, being radioactive. Um, anyways, yeah. So there's that. Oh, by the way, it wasn't discovered until later, but there's also neutrinos given off in this. And so the idea of this subneutrino observatory looking for the neutrino, this double beta decay, it's a kind of reaction. It's just what they call it because it's characterized by not having neutrinos involved in the reaction. More to be learned about that later, absolutely. But for now, it's all we need. Okay. Yeah, we'll do this one. So sample problem here, we got bismuth 214 undergoes a beta negative decay. Well, what does that mean? You just remember, you commit to memory that beta negative decay means that a neutron decays to become a proton, giving off an electron. Electrons are negative, that's why they call it beta negative, right? We could look at it as like a proton's given off, and so an electron's given off, and so overall there's no charge being given off. You might use that as a way to figure it out. So beta negative, obviously a negative's given off, so we must end up with a proton, so a neutron must become a proton. That would make sense, right? You can remember it. And so you go to the periodic table, you find the atomic number of bismuth is 83. They told us the mass, right? So you're going to write in, bismuth 83, 214, right? Like that. And then you're going to just simply make the number of protons increase by 1, right? So we have some mystery substance with 1 more proton, right? So it's going to be 1 more proton, 84 instead of 83. You just look up on the periodic table, 84. I'm looking at one right now. That is polonium. So you just go and you say, okay, well then that stuff is polonium. So, and it's polonium, the specific isotope of 214. Polonium on my periodic table says the atomic mass is most commonly 209. So this is a radioactive, it's a different isotope version of polonium. Even bismuth itself, it says, we're talking about bismuth 214. Well, bismuth 214, it's normally around 209, right? So we've got extra neutrons. So we've got neutrons that aren't stable that are decaying into protons. Right? So this all makes sense. Right. So just have a periodic table nearby to sort of look at and see with that. Let me just pause for a quick second. All right, I went and grabbed a digital copy of the periodic table I've been looking at. So there's your bismuth 209-ish, and then becomes polonium 214. Obviously, like different isotopes of these things, right? But yeah. So type 2 here of beta decay, have a positive beta decay. Okay, so in a positive beta decay is when a positron, so a positive is released. Well, if a positive is released, this occurs when a proton changes into a neutron. So picture you're losing a positive, right? So, you end up with that positive as a positron instead. So again, it makes sense. So you have a proton switching to be a neutron, but overall, same amount of charge. You got the positive on the side, you still have the positive, right? So in the decay of carbon 11, it's telling you it goes into boron. It should have, if it was done as a question, it would be like, what does it become? And you'd be able to say, because this proton, one of the protons, is going to disappear, right? Not disappear, but I mean, it's not going to be in the list anymore as a proton. So there's only 5 of them, but they're still going to have the same mass because it would have just switched into being a neutron. So what we had here was obviously 6 protons. Right there is 6 protons of carbon. And then here we've got our 6 protons, and we need to have 11 overall, so that only be 5 of them, right? 5 neutrons. And then that switches now to be, instead of 6 protons, it's only 5 protons, but balanced out by 6 neutrons. That's how the mass stays as 11, right? So that positron, that's that positive electron particle that's given off, is what results. So generically, we're always going to just reduce the atomic number by 1, essentially, and have a positron that gets kicked off, right? So that's my analysis. Same thing there, right? Just easier to see it on the fly, but prettier on the page to do in typing. One of the protons transmutates, so we have less protons, it becomes a neutron, and so on, right? And of course, that's a transmutation as well. We had carbon, ends up as boron. It's going to look different, smell different, taste different, whatever, right? Whatever you're doing with the carbon and the boron. Again, there's a neutron, or a neutrino. Oof, wrong word. All right, more practice, but again, beta negative decay. Oh, we're giving off a negative. Oh, okay, so that must be a neutron becomes a proton and an electron, because we can't change this side, right? Because this side ends up the same, and so on. I don't know if that helps or not, but I'm trying. Okay. Third type, we have electron capture. So electron capture is usually when a nucleus absorbs one of the low energy orbitals. See how in the structure of the atom, you've got your 2 electrons in the first shell and your 8 in the next shell and so on. Sometimes one of those electrons will actually get captured by the nucleus. And so when that happens, what happens here is it's a transmutation, obviously, right? And one of the electron makes one of the protons become a neutron. Okay, so one of the protons switches to become a neutron. It's almost like the reverse process of one of the other ones, right? So yeah, there you go. Oh yeah, if you're wondering like why is this considered a beta decay since a beta particle isn't given off, well, it's like, well, it still involves a transmutation of a proton due to an electron, right? So it's not always listed as a beta decay, but it's being talked about that here, as that here or whatever. But yeah, you can picture that one too. Electron plus proton produces neutron, right? So pick that as a new electron that the nucleus is picking up. One of the protons becomes a neutron. Okay. So sample problem, and this is just a hypothetical sample problem. I don't know if this one actually happens or not, but it connects into the one that the textbook kind of listed as does happen. But if you had terbium-152, so if you look up terbium on the periodic table, it is down in the lanthanide, actinide, whatever series down here. It's this one here, terbium. Okay, so it's atomic number of 65. Normally a mass of around 159. We're saying we're working with 152 version of it. Okay, so if we're doing an electron capture beta decay, we're going to reduce that proton, that atomic number by 1. So we're going to have atomic number of 65 is going to become atomic number of 66. Or sorry, it's going to this right. Proton. I might have just done this one wrong on the fly when I was switching the lesson last second here. Yeah, so that's going to be down to, oh no, that means this is all wrong. Let's switch this on the fly. So I needed to have, instead of terbium, I needed to have polonium. This needs to be, this needs to be, I could be wrong as well. Fixing this sometimes happens, I get flustered, but polonium would be the 67, and it's going to reduce, right? So that's our process here of having the new one be 1 less, and that's rated here. Yeah, so that should be good. So we're going to have polonium, and I just looked at the periodic table to see what element I was talking about here. Polonium, right? 1 less. Atomic number becomes this dysprosium we're going to see about in the next example. Okay, so this is polonium, or holmium, sorry. Not totally up on my, it was totally obscure high mass atoms apparently. Anyways, after beta decay though, so what happens to this dysprosium stuff? Am I saying that one at least right? I think so, close. That dysprosium is going to have a bunch of energy, okay? And so it gives off that energy as as an alpha particle. So it's going to be an excited state. So it's going to, not alpha particles, sorry, a gamma ray, the higher energy stuff. So it gives it off as a gamma ray. And all they show in the equation of this one, this is the easiest one to write. They're going to show a gamma ray given off by helium-3. They show helium-3 as having energy by having that little star there. The little star shows it has energy, and then regular helium-3 without the energy. There's the gamma ray that carried off that energy. Okay, so there's your helium-3. There's your helium-3 still without the energy. Okay, so this is the helium-3 with energy and without. So really easy equation there where it's literally just the same thing again with a gamma ray given off. Okay, so too easy really to, but yeah, with this high energy dysprosium, right? And it's going to give off an alpha particle, nothing changes. You've got your dysprosium 65, 152 with a little star saying there's energy, then you've got the same thing without the star. And there's your alpha particle. Right? So more practice of that, of course, knowing that nothing changes. You just basically put an alpha particle in the end. So the answer for the first one's there, but of course, make sure you can do that yourself. And that's just summary pages there, and that's it. Okay. So the simple questions here, oh, look, that's one's beta decay. Oh, you know what that is? That's the negative electron given off, and so on, right? Or alpha decay. Sorry, this one I read wrong. This one's alpha decay. I was just actually thinking, wait, is it negative or positive? And anyways, this one's negative beta decay, so it's electron given off, and a positive beta decay, so a positive being given off. Just do the things like I showed, right? Hopefully that makes sense. And